Very good. Well, thank you very much, Inigo. It's a pleasure to be here. I'd like to thank the organizing committee, particularly Said Zohdi, Manuel Nieto Vesperinas, and Inigo Fernandez and their team for organizing this great symposium in this wonderful place of Malaga and inviting all of us to be here. It's an honor for me to be part of this program. As you can see from the title of my talk, I'd like to share with you the results of some of our ongoing work on exploring what we call near-zero photonics. And in particular, we are interested to see how structures with effective parameters near zero, for example, epsilon near zero, E and Z materials, can actually have very interesting light-matter interactions. And in particular, some of the concepts that we are working on right now, which we call it photonic doping in E and Z structures. And our interest is both from the point of view of fundamental science of light in this type of material, as well as from technological point of view, looking at some of the applications, particularly in flexible photonics. First, let me acknowledge a significant contribution of 4 members of my group to the result that I'm going to present today. Inigo Liberal, who is here in the meeting, Yu Li, who just actually joined Tsinghua University as an assistant professor in electronic engineering, Ahmed Mahmoud, my PhD student, who just defended his PhD dissertation, and Brian Edwards, the research scientist in my group. Now, this conference, by the way, deals and addresses with metamaterial. As we know, one of the interesting aspects of metamaterial is how we can actually engineer the interaction of wave with matters in order to have a useful functionalities the way we would like to have. And if we look around in other fields, for example, in the field of semiconductors, we see that there are also another interesting set of possibilities that have been known and been used for a long time in controlling some of the property of semiconductor. And you're all familiar, by the way, with the electronic doping that we use all the time. In fact, the first thing we learn in semiconductor physics is that if we start, for example, with the pure intrinsic semiconductors, for example, a silicon, and it has certain electronic properties, if we go ahead and actually change, some atoms there with the dopants, then of course, the electronic property, in particular the conductivity, will change. And that's one of the foundation behind a lot of technological development, of course, in electronics. Now, do we have an equivalent photonic version of this concept? The answer is yes. Indeed, we can do something analogously for the photonic version. So in order to actually have a photonic doping, we can start with again, a pure photonic material. Unfortunately, it doesn't show up very well over here, but it's nicely seen in my screen. Then this has certain, wave propagation properties. But if you come over here and you put a dielectric particle, of course, you affect the interaction of light with these structures. Now, the question is that what kind of pure photonic materials are we talking about over here? There are many examples. One of the very well-known ones, of course, is photonic band gap structures, that if you actually operate at the band gap and you put a defect inside a photonic band gap structure, you open, by the way, photon density of state, and you have an interesting properties there. But what we have been interested is, instead of having a photonic band gap structure, to actually look at a metamaterial that has epsilon near zero properties, or E and Z. So what happens if we start with the E and Z structure and then put a dielectric dopant, so to speak, inside of that? And as you will see, by the way, it's going to have a very interesting and unusual variation to the interaction of light with these type of structures. First, as a matter of background, many of you are familiar with E and Z materials, but just to make sure that everybody in the same wavelength, is that what are E and Z materials? Now, E and Z material is materials whose real part of permittivity would be near zero at the frequency of interest, and imaginary part of permittivity would be very small. Of course, depending how small, that depends on the application you have in mind. And some of the very interesting classes of E and Z materials are as follows. For example, transparent conducting oxide, like indium tin oxide, aluminum doped zinc oxide, and gallium doped zinc oxide. And these materials have very interesting zero crossing of real part of permittivity, about 1.19 micron. And Sasha Boltaseva, Vlad Shalayev, and Otto Muskin have done pioneering work, by the way, in the area of this type of transparent conducting material. Harry Atwater has done a very interesting work with regard to how to use ITO for some of the interesting properties of that. If we go to the mid-IR, silicon carbide, by the way, is a very good example of a polar material or polytonic material whose zero crossing, by the way, happens at 10.3 micron. And the imaginary part of that could be very small. This plot I got from our collaborator, Josh Culver from NRL, whose team actually has shown that you can actually have a very, very interesting and low-loss silicon carbide materials. And if you go to the UV regime, I mean, some of the topological insulators, by the way, in the work of Nikolai Zheludev over here, that shows that around 200 nanometer wavelength, you can have, you know, some of the ENZ properties with the real part of permittivity near zero. But these are actually actual material that have ENZ properties, but these are not the only ones you can have. You can actually have synthetic material, materials that you design such that effective permittivity of that will be near zero. For example, whole class of metamaterials, stack of materials with epsilon positive, epsilon negative, for example, or metallic or plasmonic wires all in parallel, you can design it such that for at least certain particular polarization of the electric field, the real part of permittivity would be near zero at the frequency of interest. For those of you with interest in microwave, for example, you can actually have waveguide operating the TE10 mode, and near the cutoff of that mode, you actually can imitate effective properties of an ENZ structure. And of course, also photonic bandgap structure. The work of C.T. Chen from Hong Kong University of Science and Technology showed that you can actually have photonic bandgap with Dirac dispersion with accidental degeneracy that would give you effective index near zero. So there are a class of ENZ that we can do. Now, as a matter of background, I would like to show you, three properties of ENZ materials. So one of the properties of that is supercoupling that we explored about 10 years ago, and that showed that you can actually squeeze, electromagnetic energy through a very narrow channel without a reflection, with the transmission coefficient magnitude 1 and the phase 0, independent of the angle of these two ports over here. For example, in this simulation, you can see how this energy actually squeezed through the very, very narrow channel. This is supercoupling effect, and one of the very interesting properties of ENZ structures. Another interesting property of ENZ is that because permittivity, the effective permittivity is near zero, if you look at the macroscopic source-free Maxwell's equation in time harmonic scenario, you notice that the curl of magnetic field would be near zero, and that means that actually from spatial distribution, a magnetic field looks like static variation in space, but of course, it's a time harmonic field. In other words, it actually changes with time, with the frequency omega. One of the byproducts of this effect is that you actually, if you have a two-dimensional structure and you have a wave coming with the TM polarization, when the wave gets into this structure, the magnetic field has to be uniform through this cross-section, regardless of the cross-sectional shape. And that actually is a direct result coming from curl of E Maxwell's equation. Because epsilon is near zero, in order to have electric field, finite value, the gradient of the magnetic field for that particular polarization, it should be zero, which means the magnetic field has to be uniform. Now, this is independent of cross-sectional shape, so actually you can change the cross-sectional shape. The uniformity of magnetic field stays there, although the magnitude of the magnetic field can change. And one of the byproducts of that is that, of course, the effective index of refraction of the wave inside the structure would be near zero. That will give rise to a very, very long effective wavelength at the frequency of interest that you have. Now, so with this background, let's go to the concept of photonic doping and see what we mean by that. So imagine that you have a two-dimensional column of a material. For now, let me assume this is just, a simple dielectric column, independent of the direction that's coming out of the screen. And we all know, by the way, that if you actually send a wave and you have certain scattering, and if you come and you put the dielectric rod inside this dielectric structure with a different dielectric constant, obviously you can change the scattering of the structure. But if this structure starts with the epsilon near zero property and being non-magnetic, so mu is 1, you're going to see that that effect actually would be quite different. And I'm going to explain what I mean by different properties of that. So imagine we start with this column, and of course you send a wave, you have certain scattering. But now, let's get the same structure, two-dimensional structure, and put a dielectric rod inside of that. Let's say some arbitrary location inside this structure. Clearly, of course, the scattering would be different. But for the outside observer, looking at this structure and looking at the scattered field that's coming out, this structure looks like a structure with some effective permittivity and effective permeability. But here's the interesting trick. The effective permittivity stays at 0. Even though you put actually this extra dielectric column inside the structure, the effective permittivity of this would stay 0. So what does change actually the scattering of that? What causes the scattering change? That the scattering change can be interpreted as actually change in effective permeability. Now please remember this point, that none of the materials that I put over here is magnetic. In other words, these are, all of them have mu equal to 1. And yet, for the outside observer, this would look like a column of structure with effective permittivity. Stays at 0, but effective permeability will be different. Now, this is going to have other interesting features as we go through this. So let's go back to the general structure over here, and let's look at the formulation of this. This is a 2D structure again we have. You have a wave coming like this with the TM polarization that's coming like this. This boundary is an open boundary, so you have an E and Z column next to the air over here. You put a dielectric column rod over here with the permittivity positive that you have there with the radius r sub p, and you send a wave there. Now, this, of course, scatters. Now, if we go back, for example, to a mixing formula, for example, I go to Ari Civola's fantastic book and look at the well-known mixing formula, try to find out what is the effective permittivity of this column. You know, you can use the standard, mixing formula there. And this standard mixing formula, by the way, has a very interesting peculiarity. Usually, when you actually have a background host of epsilon, and you put a dielectric rod with the epsilon p, obviously the effective epsilon is the mixture of all of these, with delta being the volume fraction of the structure. However, if the background, the host material, has epsilon equal to 0, you notice that the epsilon effective is also become equal to 0. Because as you see, this epsilon h is a multiplicative constant that you have in front of there. As long as this delta volume fraction is not that high. And indeed, it's not, because you just put one column of dielectric rod there. So this is quite interesting. Even though this epsilon p that you put over here is positive, the host is epsilon h 0. From the outside world, this entire structure would look like with the epsilon equal to 0 stays there. So that epsilon effective stays at 0. But of course, something else has to change, and that is the effective permeability of this is different. In fact, going through the calculation, you'll find out that the effective permeability can be written in terms of a relatively simple formula over here. This formula does include this parameter, which is A sub h, which is the area of this E and Z structure, R sub p, which is the radius of this dielectric rod, K sub p, which is the wave number inside this dielectric rod, and the rest, of course, A is the total area that you see over here. Several interesting points about this formula. First of all, you notice that depending on the value of this positive dielectric that you choose over here, you can achieve the whole range of effective permeability. You can have effective permeability positive, very high. You can have effective permeability negative. You can have effective permeability near 0 as well. Well, that shows up, by the way, from this formula. But this formula has other peculiarities as well. For example, you notice that this formula doesn't tell you anything about the cross-sectional shape of these structures. It's actually independent of cross-sectional shape. What really shows up over here is just the area, cross-sectional area. So if you have a cross-sectional area, regardless of what shape you have, effective permeability is what you get. That's one interesting point. Another interesting point is the location of this dielectric rod doesn't matter. You can put it anywhere you want. effective epsilon, effective mu would not change. Another interesting point is that this phenomena is not a far-field phenomena. In other words, if the observer comes and sits from outside, very close to this boundary, in this region, observer would see the wavelength of lambda naught, which is in free space. As soon as observer steps inside, the wavelength is infinite, because the local epsilon is 0. But from the outside observer, even very close to this, would not know where this dielectric rod is. In fact, if you change the dielectric rod anywhere, outside observer would not notice that. And you're going to see, actually, some of the results that actually verify this point. So it's interesting that when you have over here, you can actually change what the observers see over here by changing the dielectric somewhere else. So this non-locality, and by the way, this non-locality is different than what Professor Plenary was referring to in his talk. This non-locality is because of epsilon near 0 background that you would have over here. So the way it's working actually intuitively can be explained like this. So imagine you start with the two-dimensional E and Z, and we just showed, by the way, that the magnetic field has to be uniform over here. We put a dielectric rod over here, so walking around this dielectric rod, magnetic field has to be uniform. So when you come inside of this, the field distribution inside the dielectric rod has to be azimuthally symmetric, just by boundary condition. But inside, of course, epsilon is not 0, so as a result, it has variation like a Bessel function. So if you actually take a line over here and you walk through this line and look at the magnetic field variation, you see a magnetic field variation like this. So if you go ahead and multiply the entire magnetic field point by mu naught and find the total flux of this magnetic field, you end up with this formula over here, and that will give you the effective mu. So you can actually engineer this structure such that your effective mu becomes 0. Your effective mu becomes very high, or your effective mu becomes negative, even though none of the material, by the way, is magnetic. So let's look at some examples. For example, we start with these two decays. This is a simulation that Inigo has done. And you notice you send a wave over here with this polarization. Look at what happens to the scattered wave around it. Look at what happens to the field inside. Okay, now, this is for the case that we design in order to have effective mu's also equal to 0, in addition to effective epsilon being 0. In order to be fair, we have to compare this with another column with the same cross-sectional shape, but assuming that inside that column, epsilon and mu are hypothetically both 0. Like this. Like this one. Now this one, inside, hypothetically, we assume epsilon and mu are both 0. Here, epsilon was 0, but there's a dielectric rod over here. Now what I would like you to do is just look at the field distribution outside. Identical. Identical. Even in the near field of this, identical. But as soon as you step inside, the field distribution is very different over here. Now, in fact, because the near field is the same, so obviously the far field of this will be the same, identical over here. Now, yesterday, Inigo presented in the talk that we had yesterday about the non-locality aspects of this, and he presented these 4 cases of this geometry, but for different location of dielectric rod. Please note that the dielectric rod is in different location, and yet the scattered field identical in all of this over here. Now, this is another shape we decided to do. So here, the E and Z is this bigger circle that you see over here. And then you put a dielectric rod there. By the way, this is drawn in scale. You notice that actually the volume fraction is very small of this. And yet, that very small dielectric rod can affect the scattering of that significantly. So over here, we put the dielectric rod at 3 different locations. The wave is coming from left. And let's take a look at the distribution of the magnetic field that you see over here, identical in all of them, even though you put the dielectric rod in different places, and the distribution of 2 components of electric field also identical outside. But as soon as you go inside, very different we have over there. Okay, now, so that was for the case as a case study of mu being near 0 in addition to epsilon being 0. But now that we have this interesting technique, why not actually use other interesting effective permeability? For example, could we design this dielectric rod such that effective permeability would be very, very high? So let's go back to the original structure I showed you over here. And we know, by the way, in this case, magnetic field has to be uniform. But because magnetic field has to be uniform, let's play this trick. If somehow I force this magnetic field to be 0 at a point inside the cylinder, then everywhere inside the cylinder has to become 0, because magnetic field is uniform. So what if I come over here and hypothetically put a column of perfect magnetic conductor, which forces magnetic field to be 0? As soon as I do that, the entire magnetic field over here becomes 0. So essentially, from the outside observer, this entire structure looks completely like PMC. Even though the PMC actually is only at one point or very small area, suddenly the entire structure behave as PMC. This non-local aspects of this structure is quite fascinating and can have a lot of interesting application, as you will see as we go through the talk. So, for example, here is some simulation for this. And here, if you put the actual, hypothetical perfect magnetic structure, you notice that the scattering, identical even in the near field, even right on the surface, is identical. Of course, when you go inside, the situation is different. With the hypothetical PMC, obviously the field inside is 0. You have nothing. But with this synthetic case, we do have a field inside, because this is actually a realistic scenario that we have there. And of course, the far field is the same. Now, so what kind of other interesting scattering control we can have with this, both from the fundamental point of view as well as some applied aspects of this? Okay, so we notice what's important in this two-dimensional scenario is the cross-sectional area, not the shape. So shape, you can do any shape you want. As an example, we said, what would happen if we just have a very, very thin screen? We're thinking about kind of like controllable windows. So something like this, for example. So this is the same cross-sectional area, let's say. You have an E and Z. You put a dielectric rod over here. So now, if you change this dielectric rod, you can actually change the entire structure from scattering point of view. Now, this is quite interesting. You don't need to change the entire permittivity of the structure. You just need to change the dielectric of that rod that you have over there, and then from the outside observer, the scattering will change completely. Let's test that. So we are interested in field at that point. The wave is coming from this direction. If you put a dielectric rod over here, and we look at the variation of the electric field observed at this point, as a function of frequency, you notice you have this variation. Now, at this frequency, this entire structure behaves as epsilon and mu near 0. And because you have a normal incidence, for the observer outside, inside of this looks like epsilon and mu, both near 0, would be impedance match. The wave actually goes through. That's why you get the value of the field high at this point. But if you change the frequency, you notice then you came to a point that the magnetic field on the surface of this rod becomes 0. So the entire magnetic field over here becomes 0. So this slab behaves as a PMC. Everything should reflect back. That's what transmission goes very close to 0. Again, I emphasize, you don't need to change the permittivity of all of this. You just need to change the permittivity of that rod location. And by the way, you can put the rod anywhere you want. You can put it right in the middle of this. You can put it at the bottom of this. You can put it on the top of that. This would not change. So let's look at the simulation of this. This is for the case that you operated when effective epsilon and mu 0. At this frequency, things will go through. This is when you operate it at the point that it behaves as PMC. Everything reflects back. Now, because I can have the dielectric rod anywhere I want, we can actually look at some extreme scenario. Actually, the dielectric rod doesn't even have to be in the line of sight of the wave that's coming. So let me show you this example. So imagine that you have an opaque, thick screen that you have over here. So let's say this is PEC, PEC. And you put the E and Z window over here, and you create a little bit, appendix over here, and you put your dielectric rod there. Now, the dielectric rod is not in the line of sight of incident wave, and yet still works. Let's take a look at it. This one, you operate with the dielectric that will give you the window open, so epsilon and mu both 0, wave goes through, and then Either you change the dielectric over here, you change the frequency, or you change the radius over here, everything blocks. And that's interesting. In other words, you can have a switch somewhere else, not in the line of sight of the wave that's coming, and still, by controlling that, the entire screen actually will behave differently. So how about if you make a meta-surface out of it? So far, it was only one screen. How about if we have an array of that? For example, an array of this entire structure, which essentially becomes a very thin layer of E and Z all the way, but then periodically you put this dielectric rod. And by the way, the location of this dielectric rod is arbitrary, so they don't even have to be periodic. Now here, for simulation's sake, we choose them periodic, but they don't have to be. This rod could be here, the other rod could be here, this one could be here. So as long as we have the rod per area of design, that would be enough. So if we get something like this, and we use the Drude dispersion for our E and Z, and let's say we design it such that it would behave as E and Z at 300 terahertz, so over 1 micron wavelength, let's see what happens. So here we have this dielectric rod. For a moment, we assume everything is lossless. And this dielectric rod, we choose different epsilons. And you notice as you choose different epsilons, different color will go through. So in other words, you can actually have a window made of E and Z with the dielectric rod there, and by changing the dielectric only on the dielectric rod, you can let the different wavelength go through, and some other wavelength would stop over here. Now, you might say, okay, well, this is for the lossless case, but of course, in reality, we always have loss. Let's see what happens if we add loss to this. So we're going back to the same structure, and in this case, what we did, Inigo and I looked at this parametric study. We said, what would happen? Unfortunately, the font didn't show up over here, but this is omega C over omega P, collision frequency with respect to plasma frequency. If you do it very, very small collision frequency lossless, effectively, you notice that with 1% variation of the dielectric of the rod only, you can have a variation of the transmission coefficient of 98%. But as we introduce loss, of course, Q will come down. And when we get to the loss that is actually reasonable in a sense of silicon carbide, in fact, as I mentioned, Josh Caldwell has this one, then you notice that by only 2.7% variation of the dielectric rod, you can have 21% variation of the transmission coefficient. That's still actually quite reasonable. And again, bear in mind that this dielectric rod is a very small cross-sectional area of this. In fact, in this simulation, we have used this parameter. This is 3 times of wavelength, this is 1 times of wavelength, and this is only the 10% of the wavelength that we have there. So it's a very small volume fraction of the structure. Field maps, okay, in the case of lossless, you see the magnetic field will go through. Electric field, of course, is quite high inside of this because of the resonance around the dielectric rod. If you operate it that you want to stop the wave P and C point, then you notice that, of course, no magnetic field almost go through. Most of them reflects back. And, of course, the field distribution for electric field is like this. Now, in the previous slide, I showed you that when you change the radius fix and you change the dielectric. How about if we do it the other way around? We fix the dielectric, change the radius. It still works the same way. Because remember, in that Bessel function, they go together. So obviously, this will happen over here. This is just by changing the dielectric rod. One of the reasons we are interested in that is that sometimes it might be easier, rather than changing the dielectric, to actually change the volume of this, particularly in microfluidic system. That could be quite an interesting scenario. But also, it's interesting that we don't have to have this point individually. In fact, you can put 2 dielectric rods in the same E and Z slab and try to see whether we can have 2 wavelengths will go through. Yes, the answer is possible. So in this case, put 2 dielectric rods in this scenario. You notice you have 2 wavelengths open up that you can go through here, kind of like a Fano comb structure. You can put 3 of them, 3 wavelengths can go through. You can put 5 of them, 5 wavelengths we can go through. And by the way, still, I emphasize the point, the location of these rods don't matter. You can put them anywhere you want, you get the same thing over here. As soon as you design the dielectric rod with respect to NZ, you have that. So that was so far was the 2-dimensional scenario. But then this can be extended to three-dimensional. In fact, yesterday, Inigo, in the talk we had yesterday, he showed actually the three-dimensional flexible, so-called flexible geometry cavity over here. So this is a three-dimensional version that we just showed with the dielectric rod, in this case, dielectric sphere, in the middle of this. And in fact, you can have a very interesting mode for this cavity, a mode that actually is a confined magnetic field in the dielectric rod, but distributed electric field that comes into E and Z region. And notice, by the way, this cavity is an open cavity. In other words, there is no wall between the E and Z and air over here, and yet you can have a bound mode. This is a very interesting example of bound state in the continuum for photonic structures that we have over here. And in fact, for the case of spherical shape, has been also studied by Andrew Alou's group and Mario Silverino's group, that they showed that for the circle or spherical case, you would have that. Here we show that the external boundary, by the way, could be any shape you want. And still, you can have a very interesting bound state in the continuum that you have there. Now, the cavity can have a different shape, can have a different topology, and the system still works. So by changing the shape of the cavity, the resonant frequency does not change, but the Q of the system changes. And that's actually quite an interesting scenario that we are studying with regard to quantum optics. So we have an experimental verification of this flexible cavity structure in the microwave domain at the 2.3 gigahertz domain. So we actually have three designs with a completely different shape of these structures that we see there. All of them have the same cross-sectional areas. The dielectric rod that we put over here at three different locations. So we had 9 experiments, 3 different shapes of a cavity, and for each one, 3 different locations of the rod. And indeed, experiment shows that we get the same resonant frequency. This is a sketch of the structure. This is an actual photograph of the half of the cavity that you see over here, location of the rods that you see there. And indeed, you see that at the design frequency, we get the transmission through. So resonance of this cavity happens independent of the external shape of the boundary that we have there, independent of the location of the rod that you put over there. And you get, this is the point that's essentially that EM and Z point, the point that effective permittivity and effective permeability is 0. This point is effectively the PMC point that would stop the structure there. So experimentally verify this point that I just mentioned to you about the structure in the microwave domain. So this was for the wave physics aspects of that. But can this structure have a very interesting quantum optical behavior there? In other words, one of the things we are interested to see whether this kind of structure, whether with permittivity near 0 or permittivity and permeability near 0, we can actually control the decay dynamics of an excited atom. In order to address that, first we actually ask this question, that can this structure actually tailor the vacuum fluctuation structure? Now, vacuum fluctuation is a very important part of quantum field theory, and it's responsible for effects like Casimir forces, spontaneous emission, decay dynamics, and so on. The same way, by the way, that photonic bandgap structure can actually affect and control and modify vacuum fluctuation, epsilon and mu near 0 structure can do the same. In fact, in this cartoon, we show what would happen if you have a shell of arbitrary shape with the effective permittivity and permeability near 0, what would happen to the vacuum fluctuation inside this structure? And indeed, you can actually modify that. And under the proper and ideal scenario, you can actually make the vacuum fluctuation inside of this near 0 for a single frequency. Indeed, if you look at the spectral density of this, you notice that, of course, spectral density is proportional to imaginary part of Green's function. We follow the macroscopic quantum electrodynamic approach to this problem for the dispersive and dissipative medium. And if you do that, you're going to see that there's actually very interesting dynamics that you can control for the excited atoms over here. So let me show you this. So if we put actually an excited atom, first let me just show you the distribution of the spectral density. If we have a concentric spherical shell with the permittivity and permeability near 0, and you actually follow that the spectral density that I mentioned over here, you notice that actually the imaginary part of Green's function inside of this at every point would be 0. So ideally speaking, at that single frequency, the vacuum fluctuation inside would be 0. However, if you just put one condition, not epsilon being 0, but mu 1, then at the center of that, you can have it 0. Okay, that's still very good. However, if you just have a dielectric over here, epsilon for mu, obviously that would not give you inhibited vacuum fluctuation there. So that actually we take advantage of, and we try to see how we can actually analyze the decay dynamics of quantum emitters over here. So for the interest of time, I don't show you the mathematics of that, but let me just show you some result and then we stop. So imagine that you have a shell of E and Z, and there is air over here or some dielectric there with a radius R1 and outside radius R2. What happens if we change R1 and or we change R2? What happens to the decay dynamics? It turns out that actually, depending on this R1, you can either inhibit this spontaneous emission, so atom would stay at the excited state, or as you change R1, there will be a point that you have a bound mode, so then you have a very strong coupling between your atom and the mode inside this E and Z, and that will give rise to vacuum Rabi oscillations there. So if you look at this spectral density as a function of normalized frequency, for two different radius of the internal, bubble that you see over here, if the radius is chosen like this one, then you get a almost complete inhibition of this. But if you actually choose the radius like this, then you have a very strong coupling that happens between them. Now, if we look at it as a function of time, the probability of the excited state as a function of time, you notice if that atom was in free space, you get this black curve that you see there, the standard decay that you get. But if you put it inside of this E and Z shell, you can actually almost inhibit the spontaneous emission that you have there, or you can actually make it a very, very strong coupling that happens and leads to vacuum Rabi oscillation that you see there. What if we fix this radius and then change the outer radius? Now, ordinarily, if this was a simple dielectric, if I change the radius, I'm going to change the resonant frequency of the cavity. Any cavity you take and you change, the radius of that, of course, the resonant frequency will change. But not here. This type of cavity, by the way, has a very interesting properties. That the resonant frequency of the cavity is linked to the frequency of E and Z. And as I showed you before, and Inigo showed it in the talk yesterday, then the resonant frequency of cavity is independent of the external shape of the external boundary over here. So if we change the outer radius, we do not change and we do not detune the cavity, but what we do change is the Q of the cavity. So essentially, this would be a very interesting mechanism to engineer the vacuum Rabi oscillation that you have there without detuning the cavity. And that's quite actually useful in quantum optics scenario, in cavity quantum electrodynamics. So in this one, you see that we have, what you see over here in the scale bar is spectral density of the system. The inner radius chosen at this radius. This axis is an outer radius, and this one you see there. And you notice, by the way, as you change the outer radius, this stays there at that frequency. That's one of the reasons behind this frequency independent or resonant independent of the geometry of the cavity. Now you notice there are some fringes over here. That's for the case that if you go frequency higher than omega p, this would not be E and Z anymore and becomes epsilon positive. And if you change the radius, obviously, of course, these will change. But in this one, actually stick with that oscillation there. So what you can do, actually, you can change the line width. You can change the line width of this interaction without detuning the system. So one of the things we are envisioning is that could we actually have a very interesting engineering setup that you can actually engineer the vacuum Rabi oscillation by putting a dent into this cavity. And so imagine that you have a cube of this E and Z structure. You have either a bubble over here, let's say another dielectric over here, and you have your excited atom there. And then, depending on how much you put this dent, you actually change the Q of the system without detuning the system. And in fact, in this simulation done by Inigo, you will see that over here, very nicely, you can actually detune the Rabi frequency without detuning the cavity. So the coupling stays very, very strong there, but just you're changing the vacuum Rabi frequency. So over here, as an example, we show this structure that with the outer radius 5 lambda naught, 1 lambda naught, 0.7 lambda naught, you see you can actually change the Rabi frequency without detuning the cavity. Again, I emphasize, by the way, that in this change, the resonant frequency of the cavity has not changed. What you see over here that's changing is actually the exchange of the energy from atom to the cavity and back to the atom. So that's the Rabi oscillation. Finally, how does this photonic doping actually affect the collective interaction between two quantum emitters? So far, it was one. So we know, by the way, from the decay state that if you put two quantum emitters, let's say inside a waveguide system, so this would be waveguide quantum electrodynamic system, very well-known setup. And then, of course, you can look at the photonic lamp shift, and you can look at the collective decay rate of these structures. But what we want to do is to actually split this waveguide, separate it over here, put the ENZ structure over here, put the dielectric rod as a dielectric dopant over here, create an effective epsilon and mu over here. In that case, the effective wavelength over here would be infinite, which means this entire structure should behave electromagnetically as one point. So if it behaves as one point, what happens to the collective decay rate of these two emitters, even though they're far apart? So we decided to do this calculation following these well-known formulas that you see over here. When you do this calculation and then compare it with the decay rate of this, then we are interested to look at the difference or the normalized difference between this. And then what we're going to do is that for every time that we move this dielectric rod to different location, we find that normalized difference. When you do that, you get these plots. So please look at the scale. Scale is very, very small. So this color that you see over here at every point is the location of this dielectric rod. So you put the dielectric rod at this point, you do this calculation, you find the value, you put it over here. So effectively what you see over here is there is no that difference between whether the two quantum emitters are here or whether in the near field of each other. One of the interesting points is that even if they are near field of each other, if you have actually orthogonal dipoles, of course, the collective decay will change. Whereas here, even though one dipole is like this, the another one is like that over here, still these two dipoles, they think that they are parallel with each other there. So 10 years ago, we explored this issue of supercoupling, by the way, as one of the very interesting features of ENZ properties. And now we see, by the way, that from quantum optics point of view, there's an interesting link between this structure and what we see in a classical aspect. So let me stop over here and say that actually the photonic doping could be a very interesting mechanism in really controlling light interaction with the epsilon near zero properties that can give rise to interesting possibility of controlling effective epsilon and effective mu, both from fundamental science, particularly the cavity quantum electrodynamic aspects of that in quantum optics, as well as some of the interesting aspects of flexible photonics. Because this type of cavities, as you saw, you can actually change the shape of it without changing the resonant frequency of that. Those of you who are interested, we just have a recent review over here that Inigo and I wrote for this Optics and Photonics News, a brief review. And if you're interested in one of our papers, please feel free to send me an email, and I'd be happy to send them to you. Thank you very much for your attention.
Thank you, Nader, for this fantastic and enthusiastic presentation.
Thank you.
So we have time for a couple of questions.
Thank you for your exciting talk, but I have a question.
Sure.
Let's take some preliminary figures of two-dimensional case.
Okay.
In that case, I can simply consider, for example, TE transmission of TE electromagnetic wave.
Yeah.
Yeah.
The one I did, by the way, was TM.
Okay, that's right.
Sure.
Yeah, TM. In that case, the system is exactly equivalent to quantum mechanical case. Could I consider your system with epsilon near zero as infinite potential barrier?
Good point. In principle,
in that case,
yes.
Everything becomes clear.
Yes, yeah. in principle, yes, you can consider that. Intentionally, I didn't want to say that at the beginning because, again, that matters what polarization you choose. In this case, we start with E and Z, and for the E and Z, when you have a magnetic field parallel with that, you get a uniform field. If you had a natural mu near zero material, then you could do it for TE cases. But yes, I mean, you can actually envision that that would be equivalent of that. I would not want to go through that route at the beginning of this because then, in principle, by the way, of course, any E and Z material you choose also has some little imaginary part. In some of the simulation that we have done, we have taken into account the imaginary part of it. In some application, the system would stay robust, as you saw. But one has to be careful in regard to the Q of the system when you want to do that. I'd be happy to talk to you offline for that.
Thank you for a very exciting discussion.
Thank you.
But your discussion would be valid only if you have completely uniform epsilon near zero medium.
Okay.
In reality, if you make this epsilon near zero material out of metamaterial, it cannot be uniform, and you do have some size. And how does it affect your argument?
Excellent question. Yeah, actually, if you notice from our experiment that we did, by the way, in the microwave regime, in the experiment we did the microwave regime, we used the waveguide at cutoff as our E and Z background and put a dielectric there. The system worked very nicely there. But even if you actually design your epsilon near zero or mu near zero together using the photonic bandgap structure, from the outside world, the system still works. In fact, I have an extra slide I can show it to you here. This is a design that my student Ahmed Mahmoud has done, and this actually is done based on actually a dielectric, single dielectric, but different periodicity over here, such that the side would be in the band gap, so nothing can go through, but the middle structure is actually designed using, photonic band gap with the Dirac dispersion and accidental degeneracy. And indeed, if you look at the outputs, let me show you over here if I can show it over here if this works. Okay, here. See, this port here, port here, port here, this one here, this port here, that port here, still the system works over there. In other words, if you go locally and sit at one of these dielectric over here, of course, the field locally has different epsilon. But from the outside observer, this structure looks like epsilon and mu, effectively near zero. So some of these conditions can still work there.
Yeah, thank you. I'm very sorry for this. My question was too loud. The wonderful, fascinating thing about how you can somehow switch the global response of the structure by just putting a how the permittivity, the size of this small column affects that. But I would be interested. How does the shape of this small element, does it have any effect? I mean, yes. Whatever you put there, you can somehow change the...
Yes. Excellent question. You notice, by the way, in the formula that we derived for the effective mu, the formula from the point of view of the area of E and Z was independent of the external shape. However, that formula is derived for the case of circular cross-section rod. So your question is, what happens if I go to the dopant and I change the circular cross-section rod to, let's say, elliptical? Yes, it does change. It is sensitive to that. That's important. And the reason it should change is because the magnetic field is uniform in this two-dimensional scenario for the E and Z. So when you put that dopant, the dielectric dopant there, magnetic field has to stay uniform around this, regardless of the shape of that. That would determine what should be the field distribution inside the dielectric rod, and that, in turn, would determine the frequency. That frequency should be linked to the frequency of E and Z. So yes, it is actually sensitive to the internal dielectric, and that's actually a good thing, because by changing, let's say, the shape of that, let's say mechanically, you can actually change the global system very rapidly. But if you change the external shape, it doesn't change. Yeah.
So you briefly talked about decay superradiance, but in decay superradiance there is some scaling law, right? In terms of the decay and line width and so on and so forth. Have you looked into it? Because in some sense, because the epsilon near zero is locked to a particular frequency. So how does the line width change?
Okay, good. Yeah, I mean, this is something that we are currently, looking at some of the aspect. Not that part we have not looked at in that sense directly yet. But let me tell you something. The fact is that, in reality, in some of these aspects of that, of course, it's not only very, very sharp bandwidth, because you have some loss in the system. So the loss in the system actually in that sense helps, because it gives you the line width, not necessarily very, very narrow line width, but also some line width there. So in fact, in some of the simulation that we showed over here, you notice that when we put this dielectric rod, even when you put 2, 3 dielectric rods, still system works. That's just because all those frequency that you see over there, it's about 6% bandwidth for the ENZ. So the bandwidth of ENZ is not necessarily very narrow in that regard. But the bandwidth of the EMNZ is narrow. That's true. But these are some of the aspects that, we plan to look after that later. Oh, there, I see.
Thank you for excellent talk. My question is about bandwidth. This zero happens at fixed frequency. So the response which you described was stationary. If you send time-dependent function, for example, over a system,
yep.
Of course you will see
Of course.
Please comment on this.
Sure. I'd be happy to. First of all, start with the beginning. Yes. I mean, mathematically speaking, of course, only at one frequency you have real part of epsilon near zero. However, many of the properties that I showed over here, your epsilon does not have to be mathematically zero. It can be near zero around here. So for example, I emphasize for that window example that I mentioned to you, we actually calculated from 290 terahertz to 310 terahertz in that regard. That's about 6% bandwidth over there. And when you put the rod, of course, bandwidth narrows because of being epsilon and mu near zero. So the bandwidth is reasonable, depending what you want. Particularly if you go to quantum optics, actually you want to have a narrow bandwidth, regardless of that. Now, coming back to the issue of the stationary, steady state versus transient. Obviously, of course, the entire structure is dispersive. And because the entire structure is dispersive, if you have a transient signal that goes through, obviously you have to take into account the dispersion of the structure. In fact, I do have actually one extra slide I wanted to show you over here. This actually answers your question. In this case, we actually send a Gaussian pulse over here. And when you send a Gaussian pulse over this structure and you look at the peak of the Gaussian, that will actually give you some indication of the group velocity that you have there. In fact, you notice that the group velocity, as you actually make the bandwidth narrower and narrower and narrower, group velocity becomes slower and slower. And that makes sense. If your Q is very, very high over here, it takes a longer time for the energy to go from the beginning to the end of it. In fact, this group velocity is about 1/10 of the velocity of light over here. So it depends on the bandwidth, and it depends on the bandwidth of your signal that you have there. If you send the delta function, of course, it will be a big mess. But if you send the, modulated Gaussian with the proper bandwidth, you see the system actually will go through with the energy velocity, of course, obviously less than velocity of light.
Okay, thank you very much. There is last question there.
Yeah, fascinating talk.
Thank you.
Look very thought-provoking. I presume you agree that nothing can actually travel, information can't travel faster than light.
In fact, that's the reason that here, absolutely.
And so my question actually was partially answered in the last question. But my question is, you explained how you can make your area as big as you want, okay? And you can put a dielectric in one far corner and it'll affect the whole thing. presumably, you pay for that
Yes.
in terms of bandwidth.
Absolutely.
The bigger the area, the narrower the bandwidth is,
Absolutely.
and the slower the time response.
Absolutely.
Is that right? Okay.
Absolutely, absolutely. Great point. I'm glad you asked that question so I can clarify. First of all, by the way, this entire epsilon and or mu zero structure, obviously they're dispersive. So energy obviously goes with the velocity less than velocity of light, as you can see, you know, in the simulation. But coming back to your specific question. So yes, if you keep the cross-sectional area of those two-dimension fixed, and let's say hypothetically you make a very, very thin screen like this, put a dielectric rod over here. I showed that if you change this dielectric rod, the entire system will change. But you pay a price, exactly. As you make this thing longer and longer, Q can change. And if the Q increases, by the way, and that doesn't necessarily mean that the thinner would increase the Q. Sometimes even the thicker would increase the Q. What happens is the higher Q will give rise to a lower group velocity. So this change takes longer time to be noticed at that point. Naturally, that's the case. And that's the price you pay. But if we actually look at this number as one example of that, it's still quite fast. If the group velocity is 1/10 of the velocity of light, let's say that was also the same thing, that this change over here takes about 1/10 of velocity of light to get over here. That still could be quite a fast switch over here. Albeit, of course, within the causality aspects of that. Yes. So if you make your structure bigger and bigger and bigger, Q becomes higher and higher in that regard, and it takes a longer time for the effect to be noticed from here to there. So everything is consistent with the causality, obviously.
I think that Nader has also right to have a rest. So please let's thank him again.
Thank you.